Welcome to For Science Salah Lotfy channel. This short video is dedicated to expressing our deepest gratitude and sincere appreciation. On behalf of myself, Professor Dr. Salah Lotfy, and the entire team behind this channel, I would like to extend special thanks to a distinguished figure in the nuclear energy field, Professor Dr. Tariq Farooq Nagla. Professor Dr. Tariq Nagla is the former research scientist at the Nuclear Power Plants Authority in Cairo, Egypt. His lifelong dedication to nuclear science and engineering has inspired generations of researchers and professionals. His invaluable scientific contributions to our recent video series on nuclear energy have enriched both our understanding and the content I deliver to you, my valued viewers. It was through his expert guidance and generous support that I was introduced to one of the most important references in modern nuclear science, Introduction of Thorium in the Nuclear Fuel Cycle, short to long-term considerations, published by the OECD's Nuclear Energy Agency in 2015, report number NEA number 7224. This foundational study is now the core of our ongoing video series exploring the potential of thorium as a nuclear fuel, its advantages, and its role in the future of sustainable nuclear energy. Professor Dr. Tariq Nagla, your contribution is not only appreciated, it is instrumental. I thank you from the bottom of my heart for your trust, your insight, and your belief in the mission of this channel. I will continue this scientific journey in your honor, and I invite all my viewers to stay tuned to the For Science Salah Lotfy channel as we unfold this exciting series, built on the solid scientific foundation you've helped us establish. Don't forget to like, subscribe, and share. Science deserves to reach everyone. Have you ever wondered what else could power our world besides the usual sun, wind, coal, or gas? There's a powerful energy source hidden in atoms, nuclear energy. We've mostly used uranium, but there's another element, thorium. Thorium is named after Thor, the Norse god of thunder, and it's a silvery white metal found all over the world. What makes thorium special is that it's fertile. We can turn it into nuclear fuel. Think of thorium as a log for a fire. It needs a spark, but once started it can release huge amounts of energy. Thorium is 3 to 4 times more common than uranium, giving us a vast supply. It also produces less long-lived nuclear waste, making it a cleaner option. Our journey today, follow thorium from mineral in the sand to fuel pellet for a futuristic reactor. It's a story of chemistry, engineering, and big ideas, using science to solve global problems. So, put on your safety goggles. We're diving into the science of refining thorium. Let's get started. Where do we find thorium? In a mineral called monazite, often found in heavy sands on beaches and riverbeds. Countries like Australia, India, Brazil, and the US have large deposits of these sands. Monazite isn't just rich in thorium, it's also packed with rare earth elements used in electronics and green tech. For years, thorium was a waste product from rare earth mining, but now it's seen as a valuable resource. Mining involves scooping up sand and separating the heavy minerals using spirals or shaking tables. It's like panning for gold. The heavy monazite sinks, the lighter sand washes away. The concentrate is only mildly radioactive, so miners follow strict safety rules. Once separated, monazite is ready for processing. The real science happens in the plant, where chemists unlock the thorium inside. From sand to fuel, the journey is just beginning. Next up, chemistry takes center stage. Let's see how we break open the mineral. With monazite in hand, the thorium is still locked inside its crystal structure. To extract it, we use caustic digestion, a process using sodium hydroxide, a powerful base. Finely ground monazite is mixed with hot, concentrated sodium hydroxide in a reactor vessel. Heated to about 140 degrees Celsius, the caustic solution breaks the mineral's bonds, releasing thorium and rare earth elements as metal hydroxides. The phosphate dissolves into the liquid, forming trisodium phosphate, a useful byproduct. This step is all about efficiency. Even the byproducts are put to use. The result is a slurry of solid metal hydroxides and liquid trisodium phosphate. The solid contains our precious thorium hydroxide. Next, we separate the solids from the liquid and isolate thorium from the rare earths. We've cracked open the monazite, but our thorium isn't pure yet. More clever chemistry lies ahead. The next step, isolating thorium with solvents. Let's keep going, science in action. Now we have a solid cake of metal hydroxides, thorium mixed with rare earths. To separate them, we use solvent extraction, a chemical pick-and-choose process. First, dissolve the cake in strong acid, creating a solution of thorium and rare earth ions. Mix this with a special organic solvent containing extractant molecules that selectively grab thorium ions. The thorium moves into the organic layer, leaving rare earths behind in the acid. After mixing, the liquids separate. The top organic layer holds thorium, the bottom acid holds rare earths. Drain off the bottom and you've isolated thorium. Repeat the process for higher purity. This step is crucial for making nuclear-grade thorium. Smart chemistry at work. Next, turning thorium into fuel powder. We've isolated thorium in an organic liquid, but we need a solid for reactor fuel. First, strip thorium from the solvent by mixing it with a solution that pulls thorium back into water. The clean solvent is recycled, reducing waste. Now, we have a pure thorium solution, usually as thorium nitrate or chloride. Add a chemical like oxalic acid or ammonia to precipitate thorium as a solid compound. Filter, wash, and dry the crystals. The final chemical step, calcination, heating the solid in a furnace to convert it to pure thorium dioxide. Thorium dioxide is a fine white ceramic powder, chemically stable and with a high melting point. This is the ideal form for nuclear fuel. From liquid to powder, we're almost ready for the reactor. Next, shaping the powder into fuel pellets. The transformation continues. Let's see how it's done. Our pure thorium dioxide powder can't go straight into a reactor, it needs to be formed into solid pellets. The powder is poured into a die and pressed under immense pressure to form green pellets. These are fragile, like chalk, so we heat them in a furnace, a process called sintering. At over 1,700 degrees Celsius, the pellets become dense and rock hard. After sintering, each pellet is inspected for quality and precision. The finished pellets are loaded into metal tubes called fuel rods. Fuel rods are bundled into assemblies, ready for the reactor core. This engineering ensures the fuel can withstand extreme conditions. From sand to pellet, thorium is now a powerful energy source. The journey from mineral to fuel is complete. Next, is this process safe? Let's look at the risks. Safety is always the top priority in nuclear energy. Thorium processing has two main risks, chemical and radiological. Chemical risks come from corrosive substances like sodium hydroxide and acids, handled with protective gear and sealed systems. Radiological risks stem from thorium's mild radioactivity and its decay products like radon gas. Facilities use ventilation and air monitoring to keep workers safe. Thorium dust is controlled with masks and constant air checks. The radioactivity is lower than high-level nuclear waste, making it easier to manage. Waste from refining, called tailings, is stored in lined facilities to prevent leaks. The goal: isolate waste and protect the environment. With strong safety systems, thorium processing can be done responsibly. Now, how does thorium compare to uranium? Why consider thorium over uranium? Let's compare. Uranium-235 used in most reactors is less than 1% of natural uranium thorium. 232 is almost all thorium and 3 to 4 times more common. Thorium offers a much larger, longer-lasting fuel supply. Waste is another big difference. Uranium reactors produce long-lived radioactive byproducts like plutonium, requiring storage for hundreds of thousands of years. Thorium reactors generate far less long-lived waste, its danger fades in a few hundred years. Thorium reactors, especially molten salt designs, are inherently safer operating at low pressure and with passive safety features. If they overheat, the reaction stops automatically, no human intervention needed. Thorium's byproducts are also less suitable for weapons, reducing proliferation risks. It's a fuel designed for peace and clean energy. More abundant, safer, and cleaner thorium could change nuclear power. But what would a thorium-powered world look like? Let's imagine the future. The possibilities are exciting. Imagine a world powered by thorium, not just swapping fuels, but building a new generation of reactors. The molten salt reactor, MSR, is the most promising design, using liquid thorium fuel for greater efficiency and safety. MSRs could be built as small modular units, powering towns, factories, or remote sites. This decentralized grid would be more resilient and less prone to blackouts. High operating temperatures mean more efficient electricity, and even fresh water or hydrogen production. The fuel cycle could be a closed loop. Reprocess the liquid salt, recycle unused thorium, and minimize waste. Mining needs would drop, and waste would shrink to a fraction of today's levels. To make this future real, we need more research, demonstration reactors, and public support. The promise: nearly inexhaustible, clean, safe, affordable energy for centuries. It all starts with a grain of sand and the power of science. Thorium could be the key to a sustainable future. The journey is just beginning. Let's keep exploring. Let's talk about the universe, a place of stars and galaxies, and the elements forged in their fiery cores. Among these elements is thorium, a metal more common than uranium, yet often overlooked. Thorium holds a quiet promise, a new path for nuclear energy that could be cleaner, safer, and more sustainable. Today we'll explore that path, not with wishful thinking, but with science. Thorium is naturally occurring and slightly radioactive, found everywhere in the Earth's crust. For decades it was ignored, but scientists saw its potential to unlock immense energy. Unlike uranium-235, which can sustain a chain reaction on its own, thorium-232 is fertile. It needs a push from another fissile material. Think of uranium as a match and thorium as the log that burns long and hot once lit. This difference forces us to rethink reactor design and opens new possibilities for fuel cycles and waste management. For over 70 years, uranium has dominated nuclear power, but thorium could change the game. We're on a quest for sustainable energy, and thorium is one cosmic option worth examining. So let's take a clear-eyed journey into the world of thorium. What it can do, what it can't, and what it will take to realize its promise. How do you light the thorium log? You need a special match, a new kind of fuel bundle. Scientists mix thorium with a bit of plutonium and uranium-233. Thorium is the main fuel, but plutonium provides the initial spark. As the reactor runs, neutrons from plutonium split atoms and some are absorbed by thorium, transforming it into uranium-233, a powerful fuel itself. The reactor breeds new fuel as it operates, making the thorium cycle elegant and efficient. These bundles can stay in reactors longer, extracting more energy and requiring less frequent refueling. Thorium fuel has better thermal conductivity and stability, improving safety and efficiency. It also produces fewer long-lived radioactive wastes, making the legacy of nuclear power more manageable. This isn't just a new element. It's a smarter, longer-lasting, and cleaner way to power reactors. To plan the future, scientists modeled different scenarios for nuclear energy up to the year 2100. Scenario 1, business as usual, stick with uranium-fueled reactors, no thorium. Scenario 2, evolutionary, use thorium-plutonium fuel in existing reactors, reaching about 30% thorium use by century's end. Scenario 3, expanded thorium, build new heavy water reactors optimized for thorium, pushing thorium to 70% of nuclear power. Scenario 4, revolutionary, deploy molten salt-fast reactors, MSFRs, designed to maximize thorium use and burn their own waste, with thorium providing over 80% of nuclear energy. Each scenario shows how our choices today could reshape the energy landscape for generations. What do these futures mean in practice? Let's look at resources and waste. Business as usual would require mining 15 million tons of uranium by 2100. Switching to thorium in existing reactors cuts uranium demand by 30%, millions of tons saved. With advanced thorium reactors, uranium demand drops over 60%, and with MSFRs, new uranium needs nearly vanish. Thorium cycles also reduce the total mass of spent nuclear fuel by up to 30%, making long-term storage easier. Less fuel in means less waste out, a profound benefit for sustainability. Thorium means less waste, but the waste is different. Thorium fuel produces uranium-233, which is a long-term heat source, hotter for the first few centuries. This means spent fuel needs longer cooling and special storage designs. However, thorium cycles produce far fewer long-lived minor actinides, the main culprits for million-year waste hazards. So, thorium waste is hotter at first, but its long-term danger drops off much faster, becoming as harmless as natural uranium in a few hundred years. The trade-off, more challenging short-term waste management, but a much smaller burden for future generations. How do we get thorium's benefits without the waste heat problem? Enter the molten salt-fast reactor, MSFR. Here, fuel is a liquid. Thorium and uranium dissolved in molten salt. The liquid fuel can be continuously processed. Unburnt fuel is recycled, waste is removed as it forms. Fast neutrons and MSFRs can even burn up long-lived waste from other reactors. This nearly closes the fuel cycle, offering limitless clean energy and minimal waste. It's a dream grounded in physics. A reactor that breeds its own fuel, recycles waste, and could run for centuries. So why aren't MSFRs everywhere? Because building them is incredibly hard. The materials must withstand corrosive radioactive molten salt at 700 degrees Celsius for decades. The system is complex with pumps, valves, and chemical processing in a harsh environment. Regulatory and industry frameworks are built for solid-fueled reactors, not liquid ones. Developing, certifying, and scaling this technology will take decades and billions of dollars. The road to advanced thorium power is a marathon, not a sprint. Thorium offers a compelling vision: abundant fuel, less mining, safer reactors, and dramatically reduced long-term waste. But the promise isn't a guarantee. Evolutionary steps, using thorium in current reactors, are achievable now and offer real benefits. The revolutionary MSFR is a distant but worthy goal, facing major technical and financial hurdles. The rational path is to improve existing reactors while investing in advanced thorium research. Uranium isn't the enemy, and thorium isn't a magic bullet. They're both tools. The future will likely be a mixed water-cooled reactors running on both fuels, alongside advanced reactors that close the cycle. The future of energy is one of our civilization's biggest questions. Thorium's story is complex, full of promise and challenge. Think like a scientist, weigh evidence, ask tough questions, and demand data. The path for thorium will be shaped by research, policy, and public will. Whether thorium becomes a major player or a footnote is up to us. Stay curious, keep learning, and understand the stakes. The quest for sustainable energy is a defining challenge. Thorium is just one chapter in that story. By understanding it, you help write the next chapter. Keep thinking critically. The cosmos awaits. Welcome back to the For Science Salah Lotfy channel. Today, I'm wrapping up our video series on the future of thorium in the nuclear fuel cycle, a journey that's taken us through the science, the challenges, and the long-term possibilities of this fascinating alternative to uranium. Over our past episodes, I've shown how thorium-based fuels could reshape nuclear energy. We've talked about how thorium can improve resource efficiency, reduce certain waste streams, and support advanced reactor technologies. From fuel fabrication and decay heat to reactor simulations and waste management strategies, it's been a comprehensive look at a complex but promising field. Now I want to take a moment to extend special thanks to Professor Dr. Tariq Farooq Nagla. Professor Dr. Nagla, former research scientist at the Nuclear Power Plants Authority in Cairo, Egypt, has brought deep expertise and a real passion for nuclear science to this series. His commitment to advancing nuclear science has greatly enriched these videos. I'm especially grateful to him for suggesting such a powerful and timely subject: nuclear science, introduction of thorium in the nuclear fuel cycle, short to long-term considerations. This was based on the OECD 2015 NEA report number 7224 from the Nuclear Energy Agency. His recommendations set the foundation for this multi-part series and helped bring this important discussion to viewers here and across the world. Once again, my deepest thanks to Professor Dr. Tariq Nagla. Your contribution was invaluable, and your guidance continues to inspire both researchers and science communicators alike. If you found this series insightful, please share your thoughts in the comments. Don't forget to like, subscribe, and join me here at the For Science Salah Lotfy channel for more videos where I bridge expert knowledge with the public good. Thank you for watching.